सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै।
Last time we had derived the wave equation from the three-dimensional Maxwell's wave equation, Maxwell's equations, and derived solutions for them. Let me just remind you, we started with Faraday's law and Ampere's law, without sources, there is no J, and from that we obtained the wave equation, which was and in the absence of sources in vacuum, this term simplified, and we got an equation which was del squared E minus 1 over c squared del squared E del t squared equals 0. And this is the natural generalization of the one dimensional wave equation we had already derived, which was del squared E x del z squared minus 1 over c squared del squared E x del t squared equals 0. This term 1 over c squared is nothing but mu epsilon, and for vacuum c is the speed of light. Now, at the end of this last lecture, I had talked about the solutions of this equation and how, because of the nature of Faraday's law and Ampere's law, the electric and magnetic fields are always perpendicular to z, if z is the direction in which the wave is going. Now, I am going to take one step back from all this and go to some mathematical theory. It will all connect up, which is why I am doing this, and this is the theory of the Poynting vector. The purpose of doing that is to try and make more sense out of the solutions we have been getting for the wave equation. So, to start, let us look at what we have been saying up to now. We have said that if we guessed that the electric field is E x x hat, the magnetic field is H y y hat, and if we assume that the direction of motion is z hat, then we get solutions. So, if you look at the direction z hat, it is in the direction E cross H. Now, what is more, we have seen this E cross H term coming out of doing magnetic energy, because we remember we discarded a term which went like surface integral E cross H when we were trying to calculate static magnetic field energy. So, now what I am going to do is I am going to take a look at this particular quantity, because it seems to have a lot to do with what this wave is doing, and I am going to look at it and ask what is it equal to. Well, surface integral over some surface E cross H dot ds, I can apply the divergence theorem. The divergence theorem tells me that this is equal to volume integral over the volume enclosed by the surface, divergence of E cross H dV. So, I have a starting point here where I think that there may be something interesting happening as far as the wave is concerned, but it immediately requires me to understand what is this quantity, divergence of E cross H. Now, we have got a lot of machinery at our hands. I mean, we have been doing for the last four lectures all sorts of vector identities with curls and divergences. So, let us attempt to analyze this one. Divergence of E cross H. Well, divergence is nothing but del del xi acting on E cross H ith component. So, it is del del x of E cross H along x plus del del y of E cross H along y plus del del z of E cross H along z. But I have a nice way of representing E cross H. So, what I am going to do is I am going to say this is equal to del del xi of epsilon I j k E j h k. So, this is just the same unit antisymmetric tensor and E j h k. This is the ith component of E cross H. Epsilon I j k is a constant, so I can pull it out, which means I am taking the derivative with respect to xi of a product of E j and h k. I can use my product rule for differentiation. So, I get two terms. One is epsilon I j k del del xi acting on E j multiplying h k plus epsilon I j k E j del h k del x I. So, I have just applied the derivative first to this term and second to this term. Now, let me write these out so that you can see that there is a nice symmetry to it. This is what we started with. Now, I know that epsilon I j k is cyclic. I keep drawing this figure, but I will draw it again. If I want epsilon 1 2 3, I have to go clockwise, so it is plus 1. If I want epsilon 1 3 2, I have to go counterclockwise, so it is minus 1. This just comes out of the theory of determinants. So, epsilon I j k is the same thing as epsilon j k I is the same thing as epsilon k I j. It is just a matter of whether I do 1 2 3, 2 3 1 or 3 1 2. So, I will write it out as epsilon k I j no, I won't, sorry. Let me just check. H k epsilon k I j del E j del x I. So, what I have done is I have taken the hk here, I have rotated this epsilon ijk as epsilon kij and then written out this term. This term what I am going to do is I am going to put Ej outside and then I am going to do epsilon jki rotating once del hk del xi. So, I have done nothing except this rotation. But if you look at this term, it is epsilon kij del ej del xi, which is nothing but curl of E kth component. If I want curl of any vector kth component, it would be epsilon k I j del a j del x I. So, you can see that it is the same form. This term on the other hand is again curl j k I, but unfortunately k is the index second index and I is the third index. So, in other words, I have got a matrix which looks like x hat, y hat, z hat, hx, hy, hz, del x, del y, del z. So, only in the mind we should say it, because still del x acts on hx, etc. So, obviously to get curl I want to switch these two rows, and I know that if I switch rows in a determinant I get a minus sign. So, I can identify each of these two terms with a curl. One is the curl of E, other is the curl of H. So, let me write it out. My surface integral over S E cross H dot ds is now a volume integral over the volume enclosed by the surface times H dot curl of E, because you can see the k has repeated. So, it is a dot product, minus E dot curl of H. And we have just derived this vector identity. It is that simple, which is why I never encourage any of my students to go and memorize the table of vector identities. It is simpler to just derive it. But now I have Maxwell's laws to help me. I know what curl of E is, I know what curl of H is. We wrote it out here. Curl of E is by Faraday's law minus del B del T, curl of H is by Ampere's law plus del D del T. So, if I apply it here, I get volume integral V over Vs minus H dot del B del T minus E dot del D del T. Now, actually this was an incomplete equation. The full equation said J plus. If you remember, Ampere's law was curl of H equals J, and we added del D del T to it. In doing this derivation, I threw away the J. But to do this Poynting theorem analysis, I will keep the J also. So, if I keep the J, then I will get an extra term minus E dot J. Let me write out this equation, because it is basically the final result. Surface integral E cross H dot ds over a surface is equal to minus the volume integral enclosed by the surface of 3 terms. One term is H dot del B del T, the second term is E dot del D del T, and the third term is J dot E. And this is in fact nothing but what we call the Poynting theorem. Poynting was the person who derived this theorem, and it is a crucial theorem. It is probably the most important theorem in radiation. So, why is it so important? Now, what I am going to do is look at it in 2 different ways. Firstly, let us look at what this is saying. This piece we have seen already. We can always look at this part of the integral and say its volume integral enclosed by the surface of I am going to say the magnetic stored energy in a time delta t is equal to H dot del B del T dV multiplied by dt. So, this is a rate of change of stored energy. So, I can always multiply it by dt to get a change of stored energy in a time delta t. Let me move that dt inside and I will write this as volume integral H dot dB dV. And this should be very familiar to you, because we can now integrate over time or over B. So, this will give me that the magnetic field energy at some value of B minus the magnetic field energy at say 0 is equal to volume integral over the surface, another integral from 0 to B of H dot dB. Now, I say this should be familiar to you because as electrical engineers you have been working with machines, you have been working with magnetic materials. So, you know that if you are dealing with a magnetic system, there is something called hysteresis. So, you have your H and B axes. If it were a linear system, you know that you ought to have a straight line, B equals mu H, but that does not happen. In fact, if you take an unmagnetized material and you apply a magnetic field, the curve that you see is actually very nonlinear, it saturates. And when you try to bring B down, you get a effect like this, which then gives you the standard hysteresis diagram. And you know, however you do it, whether you want to do integral H dB or integral B dH, the integral of the area enclosed by the return and the forward curves is the amount of energy that is dissipated in any magnetic system due to a cycle of applied field. So, if the applied field B were in time doing this, let us say this is time and this is B or H, then what would happen is that as H changed, magnetic field would rise and saturate, then come down, saturate, come down, come up and saturate. So, as this cycle went on, you would get a magnetic field that did not look like H at all. In fact, it showed all these signatures of saturation as well as these signatures of hysteresis. And you know very well that the amount of energy dissipated in a single cycle in time is given by the area of this curve BdH or HdB. That is where this concept comes from. This is the general form for stored energy. However, if you can assume that B is equal to mu H and mu is a constant, then you can pull that mu out and you get the standard result, which is that this whole thing will become del del T of B squared over 2 mu. So, both approaches are saying the same thing, and this is what we had got earlier. So, the first term is nothing but magnetic energy. The second term correspondingly is nothing but electric energy. We have seen this already. So, again E dot del D del T is equal to epsilon E dot del E del T, which is equal to del del T of epsilon E square over 2. So, this is rate of increase of stored magnetic energy, and this is the corresponding rate for electric energy. So, these two terms are very clear. And what is this term? This is ohmic loss, because if you apply an electric field E and if a charge moves in the direction of the electric field, then obviously there is a current J in the direction of the electric field. So, if J dot E is positive, it means positive charges are moving in the direction of the electric field, which means positive charges are going from a point of high potential energy to a point of low potential energy. So, energy is being given up by the field, 1/2 rho phi. If you like, this phi has changed. That is what is happening due to this J. But where is that energy going? That energy is going into kinetic energy of the charge. The charge is falling down a potential energy well. This is my phi. So, this positive charge is rolling down this potential well. So, it picks up kinetic energy. This kinetic energy due to collisions turns into heat. So, this is ohmic loss. So, the three terms we can see, one is the rate at which stored magnetic energy is increasing, the second is the rate at which stored electric energy is increasing, and the third is the rate at which energy is converted into heat. Now, actually it is not energy converted into heat, because this same term can also represent energy being converted from electrical to mechanical energy. If you have a motor, this J dot E term would represent the work being done to turn the motor's axle. If it were a generator, you would have a negative term here, and the J dot E would represent energy coming into the field due to the mechanical energy. So, J dot E does not really represent only ohmic loss, it represents any kind of conversion to or from non-electromagnetic energy. So, if any kind of energy that takes energy in the form of heat, energy in the form of mechanical energy, energy in the form of chemical energy, and brings it into electrical energy or takes it from electrical energy, they will all get represented as J dot E, because that is the only way by which work can actually get done. J dot E is the only place where that happens. So, we have these three terms. Now, normally what would we expect? We would expect that the rate at which stored magnetic energy is increasing, plus the rate at which stored electric energy is increasing, plus the rate at which energy is getting dissipated must be 0. That is, if you are going to dissipate energy, one of these two must decrease, or if there is no dissipation, electric energy increase means magnetic energy decrease. Magnetic energy increase means electrical energy decrease. So, this part is circuit theory. This is what we have done for the first part of this course. Inductors, capacitors, resistors and batteries. That is all this is. This is the new piece. There is a new piece here which says that on the surface, if you happen to have E cross H dot ds, these things do not add up to 0. In other words, you draw a circuit diagram, you have a battery, you have inductor, capacitor, resistors. You basically have an energy conservation equation here, namely KCL and KVL. KCL and KVL are basically telling you that whatever energy is lost in the form of IV in the battery is expended in the form of IV in the resistor, and these two do not do anything. If this were an AC source, you have an oscillating voltage which causes stored energy oscillations in the inductor and the capacitor, dissipates energy in the resistor. All of that is covered here. That is this piece: inductor, capacitor, resistor and battery. But this piece is saying sometimes it does not add up to 0, and in fact you have a deficit or an excess of energy which is showing up as E cross H dot ds. Now, if you try to do E cross H dot ds on a DC circuit, what you will find is that the electric field and the magnetic field will go in such directions that E cross H dot ds integrated over a surface gives you 0. It does not help, it does not actually violate anything. Circuit theory is still safe. The problem comes when you have waves. As you saw, we had Ex, x hat, Hy, y hat, which meant you have E cross H dot z hat, and this is not 0. Once you have this kind of possibility, then there is something new that is coming into electricity and magnetism, something that is not there in circuit theory, something that your KVL and KCL cannot capture, and it is this piece that is the crucial new piece which we call radiation. Now, let us see where we can take this further. I am going to take a circuit in a small region. So, I have some circuit, some complicated circuit if you will, and it is inside a small region V. I consider a nice surface, I am going to call it S1. This S1 fully encloses V, and in fact is quite a bit bigger than V, let us say. And I am going to apply this theorem to S1. In this region, I am going to assume it is vacuum. Furthermore, I am going to assume that even though I have drawn the DC battery and a resistor, this is an oscillating circuit. So, the voltage is oscillating as a sinusoid, it has some frequency f. So, whatever fields that come, magnetic field or electric field, they are also oscillating in time. And I am going to assume this circuit is steady state. So, whatever currents are flowing is some I naught cos omega t plus some delta. No transients, all right. Now, I want to look at what happens for such a system. Well, the left hand side is clear, but the right hand side, if I take this piece, it is going to look like volume integral over S1, Vs1 sorry, H is going to be some H naught cos omega t plus delta 1 times B naught cos omega t plus delta 1. I am assuming a nice simple system, so H and B are along the same direction. Then there will be del del t and E naught cos omega t plus some delta 2 del del t of D naught cos omega t plus delta 2 plus J dot E. This whole thing dot ds, I mean dv. This is what I have here. Now, if you look at this term, it is an oscillatory term, because del del t of cos omega t will become sin omega t. So, this will become cos 2 omega t. This will become is 1/2 sin 2 omega t plus 2 delta 1. Similarly, we have here cos omega t plus delta 2 under the derivative sign. So, it becomes sin omega t plus delta 2, and so we have cos omega t plus delta 2 sin omega t plus delta 2, and this in turn becomes 1/2 sin twice omega t plus 2 delta 2. Now, these terms involve sin of twice omega t, and if you average this function sin twice omega t from over one period, which is from 0 to t, where t is 2 pi over 2 omega, we know that sin is a periodic function, which means that this integral is 0. So, if we take the right hand side of the Poynting equation and average it over one period, that is 2 pi over 2 omega, this term goes to 0, this term goes to 0, which means that we are left only with J dot E. So, these two terms will just vanish, even though there is a term that is talking about the rate of increase of stored magnetic energy. What is happening is, half the cycle the magnetic energy is increasing, the second half of the cycle the magnetic field energy is decreasing. Similarly, half the cycle the electric field energy is increasing, half the cycle the electric field energy is decreasing. So, if I average over one time period, both these terms go away. So, what am I left with? I am left with only this term. So, this Poynting theorem then becomes integral over surface S1 of J dot E dV. But if you look at this picture, I assume that this region is vacuum and my circuit is enclosed inside a volume V. So, there are not any currents except inside volume V. So, I can write this as integral over volume V j dot E dV. Now, what is interesting about this? I am going to write it down again so that you can look at it. What is interesting about it is that the left hand side, which is a surface integral over a surface S1 E cross H dot ds, is not an integral over S1 V S1 at all. It is a volume integral over V j dot E. No matter what size surface I choose, this S1 can be twice S1, it can be 4 times S1, right hand side is still integral over V j dot E, because currents are only present inside this small region V. It is equal to constant, independent of S1. It is a very remarkable statement. No matter how large a sphere I take to do this integration, I get the same answer. So, it means if I take a sphere of radius 1 meter, I get some answer. If I take a sphere of radius 2 meters, I will get the same answer. But if I look at E and H, I know that H is equal to square root of epsilon over mu E. At least we worked that out for 1D case, it happens to be true generally. So, this E cross H is really E squared times square root of eta over epsilon. Sorry, mu over epsilon. Now, work this out. The volume in the surface integral here is 4 pi times r square, that is the surface area of a sphere, multiplied by E squared multiplied by a constant. So, it is just mu over epsilon is equal to constant. Or it is saying something entirely remarkable. It is saying E squared times r squared is constant, or E is proportional to 1 over r. At the beginning of this course, we started everything with Coulomb's law, and in Coulomb's law we saw electric field was proportional to 1 over r squared. When we added more charges together, we got dipoles, and an electric field due to a dipole goes as 1 over r cubed, and you put more and more of these charges together, it only decayed faster. We went to magnetic field, we found the magnetic field was proportional to 1 over r squared, but when you actually tried to make currents create magnetic field in loops, it went as 1 over r cubed. But suddenly, after putting all the terms that we could find in Maxwell's equations, we are finding a new electric field, and this new electric field is proportional to 1 over r. It has got nothing to do with the Coulomb law. The Coulomb electric field will give me 1 over r squared. This electric field gives me 1 over r. It is a far more powerful electric field than the Coulomb law can give me. Of course, we do not know that such a field exists. All we can say is that if it exists, then it goes like 1 over r, because for all we know, the conclusion we can draw also is the strongest field possible is Coulomb's field. Since this goes like 1 over r, this must be 0. Now, we will show that in fact that is not true, that in fact the special case we have already solved, which is the one dimensional wave equation, carries energy with it, carries power with it, and because it carries power with it, that power must come from somewhere, and that power in fact is nothing but this term. Let us look at just that, the units for this. The units for all of these are rate of change of energy, rate of change of energy density integrated over volume is rate of change of energy. So, all of these are power. Therefore, surface integral of E cross H dot ds must also be power, or E cross H has units of power per meter squared. It is also usually called an energy flux, because it's the flux of energy means the amount of energy per second per meter squared. Energy per second is power, so energy per second per meter squared will give me a flux. Now, let us see what sense we can make out of these units. Now, if we go back to Ampere's law, we know that curl of H is like current, which means H is like current into a length, current density into a length. What is current density? It is like current divided by volume, sorry, current divided by area into length. What I mean by these steps is, when I do curl of H, I am doing things like del H x, del y, which is sort of like saying I am doing H divided by some scale length in y. So, I can take that length to the right hand side. So, the unit of H is like current density times length. Current density is current per unit area. So, it is current per length squared into length, or current over length. If you look at curl of E is equal to minus del B del T, that does not give me anything, because it just relates electric field to magnetic field. Similarly, divergence of B equals 0 does not give me anything. So, we have to go to the other equation, which is divergence of D is equal to rho. From this, we know that we obtain that electric field is equal to minus gradient of potential, and therefore, electric field goes like volts per meter. So, if you now multiply E and H, what do you get? E cross H has the units of I over L times V over L, which is IV over L square. IV is nothing but power. From our circuit theory, we know current into voltage is power. So, it is power per unit area, which is what we come to from this thinking as well. These are all, these integrals all give me power. So, the total integral is power. So, this term E cross H must be power divided by area. Now, there is another important thing to look at here. As I told you, this square box is basically circuit theory. And this is the failure of circuit theory, radiation. The question is, where can the failure come from? Namely, what generates waves and what absorbs waves. Now, in general, when you ask this question, what we are asking is something more basic. There is only finite amount of energy in the magnetic field and the electric field. So, if you want to have an antenna on a tower that is generating waves so that we can listen on our transistor radios, that energy on the wave is not coming from the stored magnetic energy, it is not coming from the stored electric energy. Those energies are relatively small, and after a millisecond that energy will get used up. If energy is going out continuously, it must come from this term, it must come from the J dot E term. So, the source of radiation is again a J dot E like term. And from the point of view of the circuit, if you want to understand what this J dot E means, what it means is I have my voltage source, I have various elements, and when I do my KCL, KVL, I am finding that things are not adding up. But I know that whatever radiation is coming out is coming out of something that looks like a J dot E, and anything that looks like a J dot E has the form of a resistor. It is either a battery or it is a resistor. In this case, I can do better than that. I can say that the current that I have is itself related to the magnetic field. I will prove that later, and the magnetic field is related to the electric field. Therefore, this is going like E squared. When the power goes like E squared or V squared, it cannot be a battery, it must be a resistor. So, in any practical use of radiation in circuit theory, what is done is an additional resistor is added. So, these are the resistances, capacitances, inductances that we already have. We now add one more resistance called the radiation resistance. This radiation resistance is not a true resistance at all. It is an extra term which takes care of the fact that not all the energy supplied by my voltage source is getting accounted for in the inductor, the capacitor and the resistor. Some of it is just going elsewhere, and because I am able to show that it has got the behavior of a resistance, I model it as a new resistor, a radiation resistance, and using it I balance my equation. In other words, I make KVL and KCL come true after all. They are not really true anymore. The moment you have this term, circuit theory has failed, because circuit theory is only this side. But we fake it. We say that this piece can after all be modeled by this J dot E term, and therefore, we will just, from the circuit theory point of view, we will just add a new resistor. It is a frequency dependent resistor, it is a resistor with very strange properties, but we will pretend it is just a normal resistor, and we will be able to balance our equations, we will be able to use circuit analysis and get answers to our problems. All right. So that led me to an important question, which is, how do I claim that J is proportional to E? And for that, I must go back to the wave equation that we looked at. Let us write down Maxwell's equations. You have Faraday's law, then you have Ampere's law, you have the divergence theorem for electrostatics, and you have that the magnetic field is divergence free. Now, as far as we know, these equations are exactly correct, which means there are two equations which have not changed at all from statics. These two equations are exactly what they were even under statics. It's only these two equations that have changed. Now, if you think back to what we did in electrostatics, what we said was, if there is any material and if there is a region where you have a change in dielectric constant, then all I will do is I will take an imaginary surface in the shape of a cylinder, and I will take the surface such that this height h is much smaller than the radius of the top and bottom, which are pi, say, a squared. So, I am going to assume h is much less than a. I can always do that. It is my surface, so I can create any kind of surface I want. Then I look at the displacement vector on both sides, and I apply the divergence theorem. So, what do I get? I get volume integral divergence of D is equal to surface integral D dot ds is equal to Q free enclosed. At this boundary, I do not have any free charge, so I can set it to 0. But if I did have free charge, I have to keep this term. Now, this surface integral involves an integral over the top, involves an integral over the bottom, and involves an integral over the sides. By choosing h much less than a, I can make the sides negligible. So, it is only the top and bottom, which tells me that dn1 minus dn2, that is, if this is dn1 and this is dn2, if I take these two quantities, one is pointing up, so positive, other is pointing down, so I put a minus sign to indicate it is negative. This is the times the area is nothing but the enclosed free charge. But what is the enclosed free charge? Enclosed free charge is rho free times dA. So, that gave me a condition for d normal, which was d normal 1 minus d normal 2 was equal to rho free. The same kind of analysis for magnetic field gave me B normal 1 minus B normal 2 is equal to 0. These we had done in statics, electrostatics and magnetostatics, and these arguments are still valid. Even for waves, even for time dependent fields, these two conditions still hold. But when we ask about the first two equations, we have new terms present, and we have to worry about what those terms are doing. Now, if you recall, we again used for electrostatics epsilon 1, epsilon 2. I used a Stokes curve. Once again, the height much smaller than the length, and integrated loop integral E dot dl. This loop integral is equal to E tangential 1 minus E tangential 2 times L. But it is also equal to the surface integral curl of E dot ds, which is connected by Faraday's law. So, it gives me minus d dt of surface integral B dot ds. But this is a very tiny loop, and I can make this loop get really small, taking care that h is much smaller than L, in which case this goes to 0, which means E tangential minus in region 1 minus E tangential in region 2 is equal to 0. The fourth equation I will do next time, but that fourth equation is the one I really want for proving J dot E has the properties I said, and that will tell us that this quantity that we are talking about, the E cross H, is really an important quantity. It is not some kind of fiction of the mathematics. In fact, you can have systems which generate this E cross H, and you can have systems that absorb this E cross H. And once you have those two ideas, then you have all the foundations required for understanding radiation and optics.